Alright guys, just doing an alpha response video in respective moments. I'll cover these more in depth later, but for now we're just kind of going to look at them a little in depth and hopefully give it a little bit of a patch job. Okay, so we have a straight bar, and at point A it's fixed to the wall, but you know, it can kind of spin around, but it's kind of stuck there. So you have a force here. We're assuming there's no gravity in this situation, so just ignore gravity. There is a force here of, you know, I don't know, A. No, that's bad. We've already got A. There's a force of, we'll say 20 newtons. Okay, so if you have it fixed here, but it can kind of turn, you know, and you have a force acting downwards on the bar, which way is the bar going to turn? You kind of intuitively say, well, if you're kind of pushing down that way on the bar, it's probably going to start spinning around that way. And, you know, that's correct. So, what we do this, is you can kind of intuitively look at most questions and kind of figure out which way. Otherwise, you can use the right hand rule. And the right hand rule is pretty simple. You just line your wrist up where the distance starts, point your hand along the distance, and then you curl your fingers in the way of the force. So since the force is going this way, I'm going to curl my fingers that way. And whichever direction your thumb is facing, you make a thumbs up, is whether it's positive or negative. So if your thumb is facing away from the board, that's going to be positive. And if it's going into the board, that's going to be negative. So if we replace this vector with a vector going this way, and we do the same thing. You start your wrist here, line your hand up, and then curl your fingers in the way of the force. Well, the force is going that way, so to curl my fingers in the way of the force, I have to turn my arm around and go that way. So if I make a thumbs up, it's going to be facing into the board, right? So that's going to be negative. Once again, you can kind of intuitively look at that. I'm going to go, well, it's going to go this way. And for most situations, this way will be counted as negative, whereas this way will be counted as positive. So clockwise is generally negative, and counterclockwise is generally positive. And, you know, you can kind of relate that, like, if you imagine, like, a screw, if anyone's, you know, kind of woodworks, if you screw it this way, it's going to come out of the timber. So if you screw, you know, righty-tighty will go into the timber, and lefty-loosey will come out. So that's like a, you know, maybe another way you want to remember. There's a lot of ways to remember, and it really comes down to you. Okay, so let's consider that the bar can't move at A, right? It's completely fixed there. Someone's maybe, I don't know, holding it. Just supporting it. And they're holding this, so it can't move. If a force is acting here, and there's no gravity, it's probably not going to be that hard to hold up. But if the force was acting maybe down here, you can imagine that that bar is going to, you know, kind of tilt down really far, and you're going to have to really be holding on it. So what you can see is the length is going to make it more difficult for this guy to hold it up. So what we do here is, this is called a moment. That's how much this point wants to spin. Because even though he's holding it and the weight's over here, the whole beam's not going down. It's just trying to spin. And that's because, you know, the force on the beam is still going to equal to this, right? So the total Y force is going to equal this plus this. But the spinning motion, which is called a moment, is equal to this force times this distance. So, you know, if this was 2 meters, and this was 10 newtons, you'd have a moment of 20 newton meters. And you go, well, is this positive or negative? Well, it's going this way, which is anti-clockwise, so that should be positive. You can use the right-hand rule to check, you know, start over here, going that way, thumbs facing out. Yep, so it's definitely positive. So you can have a positive force of 20 newton meters. Whereas, if the force was acting over here, halfway, at the same thing, 10 newtons, well, now it's only going to have a distance of 1 meter. So then you're going to get 10 newtons times 1 meter, which is 10 newton meters. And once again, that's going to be positive. So you can see with the distance, the larger the distance, the greater the moment about A is. Okay, so we get rid of that and draw up another image. Okay, so you have a guy. Don't know why I'm liking people. I'm just feeling in the mood for drawing some people. Okay, and he's supporting a bar, right? And once again, there's no gravity, so just ignore gravity. There is a force going this way on him, on his bar, and that's 10 newtons. This is 2 meters, and this is 2 meters. Okay, so the moment about this point is going to be equal to the force times the distance. And remember that the force must always be perpendicular to the distance. So this angle in here will be 90 degrees. And we can probably look at that more later if you... Well, we'll probably look at that more in the actual video about moments. For now, this is kind of just a patchwork. Just remember that if this is going to be going vertical, then the distance has to be horizontal. If the force was horizontal, then the distance would have to be vertical. So as long as you kind of resolve all your forces and distances into horizontal and vertical components, there shouldn't be an issue. Okay. So you can kind of imagine that this is going to be trying to spin the wood clockwise, which is negative. And you got 2 meters by 10 newtons. So that's going to give you 20 newton meters. And that was going to be negative, because that was clockwise. And, you know, you start your wrist there, go there, curl your fingers. Yeah, my thumb's facing in the board, so it's definitely negative. Okay, so we kind of want this guy to be balanced. So how are we going to balance his load? Well, if he's got a force going down there, you might think, well, let's put force going up here. And, you know, that might work, you know. But if you kind of imagine the pole being twisted that way, the first thing it's going to want to do is spin around the middle. And if you kind of line your hand up, once again, that's going to give you a negative force of 20 newton meters over here as well. And what we do, we can just add forces. Like, it's not difficult. This is negative, so you're going to get a total of negative 40 newton meters. So we just made this guy's life a whole lot worse by adding in the second force. So let's get rid of that and kind of spare him some trouble. Okay. So to balance out this force, we're going to get a force over here. Once again, that's going to be at 90 degrees. That should be 90 degrees in here, wouldn't it? Won't really matter, but whatever. Okay, so that's 10 newtons. That's 2 meters. We already worked out that was negative 20 newton meters. This one's going to be 10 newtons by 2 meters again. And it's going to be positive, so plus 20 newton meters equals 0 newton meters. So this thing is not trying to spin at all. So you're thinking, well, you know, so what? He's just standing there kind of holding a point that's not trying to do anything? Well, no, it is trying to do something. It's just not trying to spin. Because this one's trying to spin it this way, while this one's trying to spin it this way. So they're going to cancel each other out. But the total force on him is still going to equal 10 newtons. Remember this, the sum of all the y forces acting on this beam will equal negative 10 newtons, minus 10 newtons, that's negative 10 as well, plus whatever he's putting on the bar. So plus, you know, force A. And that will all equal 0 if the bar's not moving. Because, you know, if it equals negative 20, the bar would be going down. Yeah, you probably should know how that works by now. Okay, so basically that will give you force that he has to put to keep the bar at 20 newtons. And that's not so hard. So it's not spinning, it's not going up and down, it's just having a nice time. Okay, another thing to do with moments is two force beams. So there's only two forces acting on this. One force acting here, one force acting here. No, we'll use a straight line. We'll make it even simpler. Let's keep it nice and basic. You know that by Newton's law, the forces on it have to be equal and opposite to keep it in equilibrium. So let's do that. Let's place, you know, a force here and a force here. Yeah, they're equal and opposite, but it's not going to be in equilibrium because they're both spinning the bar around. So this is going to keep spinning faster and faster until, you know, I don't know, I guess it breaks the speed of light or something, and that's bad. So that's not going to be in equilibrium. So we can rule that out. Okay, so how are we going to make this in equilibrium? Well, maybe we can like make it at an angle, like that's there, and that's there. They're still equal and opposite. Well, what way is this going to be spinning? What way is this going to be spinning? Okay, so we'll break this into its horizontal components. Okay, so that's that one's vertical component, horizontal component. That's its vertical component, its horizontal component. Okay, so its horizontal component is going to be pulling the bar that way, so it's not going to be spinning the bar at all. And why is that? Well, if you take the horizontal force and times it from its vertical distance, and we'll call it at this point here, well, how far is it vertically displaced? Well, it'd be 0 meters. So even if this was like, you know, 2,000 newtons, if it's times 0, it's always going to equal 0. So that's just going to cancel out. That's probably a confusing way to explain this. This isn't really a well-prepared video. This is just a response. These are generally pretty casual. Okay, so that's not going to work. Because those vertical forces would still have just been spinning it. Probably should have said that before I rubbed it out, but tough. Okay, so to balance these, the only way, well, there's two ways actually. Well, sort of the same way. The only way that these forces can remain equal in the y equals 0, x equals 0, we'll call that A, we'll call that B, and the total moment equals 0. Now, the moment at B will always be equal to the moment at A. At any object in the system, the moment's always going to be the same, because if one object's spinning, then everything else is spinning at the same time. So, don't worry too much about what you choose. You can make that moment about A, or you can make that moment about B. We're going to choose B, because I don't want to write over that again. Okay, so if we had a force going this way along the member, and a force going this way along the member, well, you know, this could be 80 newtons, and this could be 80 newtons, and they're going to cancel each other out, so we're going to have x of 0, yep. There's no y, so yep. And the moment they're going to cause, well, their vertical displacement is 0, and we're taking their vertical displacement because these are horizontal vectors, so perpendicular to them will be vertical displacement, which is 0. So, you know, 0 plus 0 is going to equal 0, so that's fine. And we can say that these vectors are in line with each other, or they cross the lines of action of each other. And that's a pretty important concept, because, you know, that's going to be in the module, so you should really know that one. So to stop this from rotating, these have to be in each other's line of action. So what's a line of action? Okay, well, a line of action basically says, if a force is going this way, its line of action will be anywhere along there, anywhere along here. If a force is going this way, its line of action is going to be anywhere along there, anywhere along there. You know, if it's going this way, anywhere along there, anywhere along there. Okay, so that is a basic rundown of moments. And I know I said that the two-bar member, actually, I know that they said they had to line each other's path. So, you know, if that's going this way, and this one has to be going this way, you know, to kind of balance that. But there is one exception. And these are parallel lines. If you had a weight here, and a weight here, and a force here, force 1, force 2, force 3, These are never going to cross each other's lines of action. And if we took the moment about here, that's going to equal, all those moments are going to equal each other out, and there's going to be no moment about A. So even though they would cross each other's line of action, these two are going to be pulling it that way, and that's not going to be creating any moment. That's just going to be pulling it up to counter those two. So that's not an issue. And I know what you're thinking, so what? Well, you're probably not thinking it, but you should be thinking it. Okay, so I'll write out these lines of actions. So if I took the moment about point A, right? I have a force, going this way, a force going that way, so those two are going to cancel each other out. Let's just say, this is 20 newtons, this is 1 meter, this is 1 meter, this is 20 newtons. So to cancel out these, because the sum of all y has to equal 0, so negative 20 plus negative 20 plus f2 equals 0. Therefore, f2 equals 40. Okay, so that's the first thing. We got no x vector, so we can just ignore that. Okay, so the moment about point A is going to equal negative 1 times 20 Newton meters. Just check that's okay. Alright, that seems a little dodgy, but that should... that'll be fine. It's not too much of an issue. Okay, that's going to be negative 20 Newton meters. That's going to be positive 20 Newton meters. So that's just the force times the distance. And it's going to be positive because my thumb's sticking out of the page, and, it's spinning anti-clockwise. So that's about this. So that's going to equal 0. That's going to be fine. And that's about point A. However, we took the moment about something like point Z over here. Well, we have force going this way and a force going that way, but they kind of have different distances. But if we look at it, it's not that much. It's not that different. This is going to cancel out because it's going to be 0 because it's vertical distance. So you got to take its horizontal displacement from Z, which is going to be 0. So it'll be 20 times 0. And once again, I'm going to go all over this in my actual video moments. This is just a quick response to try and help someone out. Okay. So to calculate the moment about Z, we got 1 meter times 40 newtons, and that's going to be positive. So that's 40 Newton meters. And we got 20 newtons times 2 meters, so it's going to be 2 meters away from Z. It's going to be that total distance. So negative 20 times 2 is going to be negative 40 Newton meters, and that will equal 0. So even though these don't cross each other's lines of action, they will still be in equilibrium, and that's an exception for parallel lines. Alright, so I hope you enjoyed my video, and I'll try to get my actual video moments up as soon as possible.